Welcome you to this lecture on wave motion. Particularly, this is part of the course of the marine hydrodynamics under the NPTEL program. In the last couple of lectures, we have talked various aspects of water wave motion. Today, we will try to work out a few examples and to illustrate some of the applications or for better understanding of these wave motion problems. So, let us start with a very simple example. Suppose a wave in water of 2.3 meter deep. So, let me call this example 1. A wave not of 2.3 deep has a period of 10 seconds and height of 2.3 meter. Now you need to calculate wave celerity and length. Basically, I mean the wavelength. So, this is the question. So, in this case what we will do, because if you look at omega square for any wave, the dispersion relation is omega square is gk tan hyperbolic h. Suppose because I have a wave in 2 meter deep, water depth is very small and period is 10 seconds. So, and it has a height of it is 2.2 meter. So, if it is height is 2 meter, whereas the water depth of water, that means h is given as 2.3 meter and capital H, which is the water wave height, that is 2.0 meter, and we have given t as 10 seconds. If I assume suppose I assume shallow water. If I assume shallow water waves, this water wave I assume it is of shallow water waves. If I assume this, then what will happen? Then as per definition, c square is gh and c square is the h is 2.3, 9.8 into 2.3, and this is c, that is meter per second, and that becomes 4.75 meter per second. If c is this, then what will happen to c is nothing but c is equal to lambda by t, and lambda by t is 10, because it has given t is 10 seconds. So, this becomes 4.75 meter per second, and which implies lambda is equal to 47.5 meter per second. So, this is my lambda. So, wave celerity, we have already seen wave celerity and wavelength. Now, I have started with the assumption that this is shallow water case. What will happen in case of shallow water? Then it will be h by lambda will be, if it is shallow water case, so my h by lambda will be 2.3 divided by lambda is 47.5, and this ratio, this is give me, it can check it 0.048, and this is less than 0.05. So, this is satisfied and the assumption. So, this is satisfied. So, h by lambda is less than 0.05, which implies this is the case of shallow water waves. Case of shallow water wave. So, I have started with an assumption shallow water waves, and I have also, so this assumption is a justified assumption. So, I can always say the assumption is justified. So, this is true, that means this is lambda is 47.5 and this c is 4.75 is true, because the assumption is a valid. So, because of this because of this assumption, and this becomes easy, and then otherwise I would have solved this equation. Original equation was this omega square, but this has simplified to a large extent the problem. Now I will go to another example. And we call this as example 2. Suppose a wave in water of 100-meter deep has a period of 10 seconds and a height of 2 meter. Then it is saying determine wave celerity, determine the wave celerity, length, basically I mean here the wavelength, and stiffness. So to do that, what I have to do, I assume because it is a 100-meter deep water, my h is around 100 meter, and it has a period of 10 seconds, t is 10 seconds, and height of capital H is 2 meter. So if I assume the case of deep water, assume the wave motion is in the case of deep water waves. If I assume that it is a deep water case, so when you have omega square is gk in case of deep water, which can give me easily that I can easily get it from lambda is 1.56 into t square. This if you put omega is equal to 2 pi by t and k is 2 pi by lambda, then one easily get this from this equation. So I have been given t is 10 seconds. So if I put t is equal to 10 seconds, then the lambda is 156 meter. And again, if lambda is 156 meter, then I will look at h by lambda. H is 100, lambda is 156, and that is greater than half. Hence, this assumption of deep water, the deep water assumption is justified. Is valid. Now once this is valid, now what I have been asked again, then I will say what is my c. C is nothing but lambda by t, 156 by t is 10, so this is 15.6 meter per second. Then again, and wave stiffness, that is your h by lambda. H by lambda, h is given as a 2 meter, lambda is 156, and that gives me 0.013. That is my h by lambda, that is the wave stiffness. And this is c. So we have a c is 15.6 meter per second, and we have lambda is 156 meter. So initially lambda is this, c is this, and h by lambda is this. So here in these two examples we have seen the assumption that whether it is a shallow water assumption, because fortunately we are lucky that our assumption has become justified, so that easily we could do this calculation. On the other hand, if it will not be satisfied, either suppose this assumption will not be a valid assumption, and if it will not be valid, this will not hold good, this condition will not hold good. In that case, I may have to solve the original equation to find what exactly the wave behavior. Right? I have been tried to search tan hyperbolic this relation. This is the water wave dispersion relation. So, and often we have to approach the numerical methods. Even if in the previous case it was possible, because we are able to handle it directly, because the assumption of shallow water was also valid assumption. So now with this two simple example, I will go for another example where the propagation of a wave from deeper water to shallow water. Let us see what another example of a wave from deep water to shallow water. Suppose in the last two examples we have seen that wave propagate, there is no change in water depth. Now suppose I have a wave, suppose I say wave in water of 100 meter deep has a period of 10 seconds and a height of 2 meter. When it propagates, when it is propagated to into a depth of 10 meter, when it is propagated into a depth of water of 10 meter without any refraction or without refraction, let us determine the wave height. And the water particle velocity. Water particle velocity and pressure at a point meter below the at a point 1 meter below the wave crest. Sorry, 1 meter below the still water level under the wave crest, under the crest. So that means I am looking at, if this is mean water level, so I am looking just at this point. If this distance is 1 meter below the water depth, my initial water depth, so it was initially the depth was 100 meter, this depth was 100 meter, h was initially 100 meter. So in this case what will do, if you look at this omega square is gk, assuming that this is the first, initially it was in the deep water wave regime, then we all know that lambda is equal to 1.56 into t square and t is 10 seconds, so it will be 156 meter. So lambda is 156 meter initially, and this wave was propagated. And if you look at this assumption, because I have taken this under the assumption of a deep water, this is under case of deep water, and we have just in the previous example we have seen that this assumption is a valid assumption because h by lambda is 100 by 156, that is greater than half. So this is a valid assumption. Now when this wave has propagated to a depth of 10 meter, then what will happen? Then if we look at our original equation, omega square is gk tan hyperbolic kh, we have been given t is equal to 10 seconds and our h is 10 meter. If h is 10 meter and g is 9.81 meter per second square, then you can easily see if you substitute for t is equal to, that is here omega is 2 pi by t square is equal to g into 2 pi by lambda to tan hyperbolic 2 pi by lambda to h, and if you substitute for t, g and h, then find the solution for lambda, then one can easily see that lambda will be 93.3 meter. This will be lambda. It can be checked. One can apply the fixed point iteration method or the bisection method to find this lambda from this solving this one, because t is known, h is known, g is known. Once this is lambda is known, then we have k is equal to 0.0673, because k is nothing but 2 pi by lambda, and it is meter. That is my wavelength, a wave number, and then my n is, in general, n is equal to 1 by 2 1 plus 2 k h by sin hyperbolic 2 k h, and this gives me, if I substitute for k and h, that will give me 0.873. So, in fact, we know that n is equal to half in case of shallow water, in case of deep water where n is equal to 1, in case of shallow water. So, this n itself, the value shows that it is the case of intermediate water depth 0.873, because it lies between 1 and half and 1. Now, again if you will go back to energy conservation laws, ECG is equal to constant, where CG the graph velocity is the energy density associated with the wave. Then we have from this CG is a c into n into E is rho g h square by 2 by 8, and that gives me c is nothing but lambda by t, and this is n, this is h square, that is equal to constant. Because at the period of the wave is same, then I can always say that lambda n h square is equal to constant. So, if I take this value as of, that means lambda, that is lambda n h square at h is equal to 100 meter is same as lambda n h square, and that is h is equal to 10 meter. Because initially the wave was in 100 meter deep, and then it has come back to a depth of 10 meter. So, if I substitute for, and in case of when h is 100, I have seen that, we have seen that this is the case of a deep water. So, in case of a deep water, n is equal to half, and in case of when h is 10, we have already seen n is equal to 0.873. Substitute for n from both sides, and the initial wave height was, we have initial h 100, the wave height initially it was 2 meter, and my lambda was 156 meter. So, this was lambda 100, and then I have seen that my lambda 10 is 93.7. So, my lambda I have seen 93.3 meter. So, if I substitute for these values, this and this with along with this, then I substitute here, then I will get my h10, the wave height at the when the at the depth of 10 meter, that will give me, I substitute 1.97 meter. This is the wave height. So, there is a small reduction in the wave height from 2 meter to 1.97 meter. This is what, and this we have obtained by this result, and this is nothing but the energy conservation of energy flux. Now, again to evaluate near the crest, because I am interested in knowing the pressure, I have P is, if I apply the Bernoulli's equation, P is minus rho g y plus phi t minus phi t P by rho, and if this is the case, then I have eta is, suppose I assume eta is equal to a cos kx minus omega t, then my phi will be a g by omega cos hyperbolic k into h plus y, a g by omega cos hyperbolic k y cos hyperbolic k h into sin kx minus omega t, and then we have this. If we substitute for eta and phi and p, and again y is equal to minus 1 below the crest means, so this will give me, my p will give me, it can be easily see that 19,113 Newton meter per meter square. So this will give me the pressure, hydrodynamic pressure. And again, if I look at, calculate the horizontal velocity, particular velocity, because phi is there, so phi is, u is nothing but phi x, and then below the crest 1 meter, below the water waves, below the crest, this will give me 1.01 meter per second. So this can be checked by substituting for these values, and then this will be, one can easily obtain. So we have the 3 examples what we have solved. First case we started with a example, very simple example of a shallow water waves, and then we went to a case of a shallow deep water waves, and then the third example is very interesting, because here we are able to know the how the water depth changes due to the change in, how the wave height changes due to the change in water depth, and also how one is able to calculate the pressure and the components of velocity, particularly the horizontal and vertical component of velocity of the water particles. This is a very clear example. In a similar way, one can work out many such examples, but with this understanding, I will just go to work out a little more theoretical problem. Particularly, let us look at the capillary gravity wave motion. One problem associated with the capillary gravity waves. The problem is like this. So we all know that in case of capillary gravity wave, the dispersion relation is omega square is gk one plus mk square, whereas, or sometimes we call it, whereas m is t by rho g. This is the, t is the coefficient of surface tension, g is the gravitational acceleration due to gravity, rho is the density of water, and omega is the wave frequency, whereas k is the wave number associated with the capillary gravity waves. And sometimes we put it in this form, we call it capital K is equal to k into 1 plus mk square, whereas capital K is also omega square by j, or into tan hyperbolic case in general. Now, what will happen in case of deep water? When k h is much larger than 1, then we get k is equal to small k into 1 plus mk square, and if k is this, k is nothing but omega square by g, and that will give me omega square is equal to gk 1 plus mk square, and then omega square by k square g by k 1 plus mk square, which can be written as g by k plus gm by k square. By k, gm into k, and if I say this is nothing but c square, so what will happen to T c dc by dk? if I take the derivative with respect to k, then this will be minus g by k square plus gm. And if I say this is 0, that means c is not equal to 0, dc by dk is 0. That will give me optimum value. Once dc by dk is 0, which implies that m is 1 by k square, implies k is 1 by root m. So, it can be easily seen that for this value, for k is 1 by root m, the c will attain a minimum. It can be checked, because this will be optimum, either a minimum or maximum, but it can be seen that when c is equal to, when k is equal to 1 by root m, c becomes c minimum. So, this can be checked, and once this is there, when k is root m is t by rho g. So, this will be rho g by t. So, that is c is equal to c minimum. So, what is that c minimum? I call it Cm, say. So, c is equal to, because this is basically we are considering the case of this is the case of deep water. So, Cm square is equal to g by k m 1 plus this is g by k into 1 plus km square, and that will give me. So, if I take g, mkm square is 1, because k is 1 by root m, km is 1 by root m, so c is equal to cm. So, mkm square is 1, so that will be 2g by km, and that can give us, and then again km is rho g by t, 1 by k is equal to, for c is equal to c minimum, this is rho g by t, so t by rho g. So, that will give me 2g into t by rho g, and that will give me, because there is a gt by rho, if I put it this way. So, this will give me this. So, Cm, that means my Cm, C minimum becomes this 4 gt by rho, and my Km is equal to 1 by root m, which is nothing but rho g by t. So, for this k is equal to km, c becomes cm, that means minimum value of speed of the flexural of the capillary gravity waves that comes up, and that means, and then if I just take one typical case, that if I take g is equal to 9.8 meter per second, then rho is 1000 kg per meter cube, and t is equal to 0.074 Newton per meter, then we can see that C minimum is equal to 23 centimeter per second, and whereas corresponding lambda m, because km is this, so lambda is 2 pi by km, and lambda is 1.7 centimeter. So, for these values of these parametric values, we can get Cm is 23 centimeter per second, and lambda is 1.7 centimeter. That means, when a wind blows, this is the minimum speed which can attain. Below that, there will for this, in this case, when the particular gravity waves, when a wind blows, begins to blow over a flat sea surface, no wave will be possible below this c is equal to Cm. When c is less than Cm, no wave motion will be possible. because it is the minimum, the speed is minimum here. So, below that no wave motion is possible, and in fact, it has been pointed out that perhaps that is the smallest possible wave among all wind generated wave. This wave, this lambda wavelength lambda and the corresponding Cm is perhaps the smallest possible wave that exists in the ocean, particularly when you look at the gravity waves or the wind generated waves. So, this is one of the very important example of the wave propagation problem. So, shows that how small a wave length can be 1.7 centimeter, very small. Now, this is one aspect. Let me work out another case in the same line, that is suppose I have been given omega square is a gk 1 plus mk square tan hyperbolic h. This is my dispersion relation. So, what will happen here from 2 omega d omega by dk, and that will give me g by this is my both sides derivative I have taken, and when I take the derivative, after a lot of simplification I can always get d omega by dk is equal to 1 by 2 omega by k into 2 kh by sin hyperbolic 2 kh plus 1 plus 3 mk square by 1 plus mk square, and that same as this is nothing but c by 2 kh by 1 plus mk square. So, this is my d omega by dk, that is Cg, and this definition is the Cg, that is the group velocity associated with the capillary gate waves. This is one of the most general result for the, and if I say that kh is much greater than 1, then this quantity will be 0, then my Cg will be c by 2 1 plus 3 mk square by 1 plus mk square. This will be c by 2 into this, and then this further can be simplified to write it 1 by 2 into g by k root over to 1 plus 3 mk square by root over of 1 plus mk square. This is your Cg, and it can be seen again if I assume that Cg will be minimum. So, if I say that dCg by dk is 0, that will again give me Cg minimum, and it can be seen that in case of deep water, when kh is much greater than 1, then Cg is equal to Cg minimum, that means group velocity will attain the minimum only when mk square 2 by root 3 minus 1. For this value, this Cg is minimum. Now, you go back to know that what exactly happened. It has been seen that for water at 20 degree Celsius, we can say that rho is equal to 1000 kg per meter cube, and we have T is equal to 0.074. The same example, Newton per meter. Then it can be initial that in that case the Cg will be 17.8 centimeter per second. That Cg is Cg minimum. So, this is what happen in case of a deep water, this case. So, this is one of the another example which suggests me that how the wave propagation, how the group velocity can be obtained, also minimum in the group velocity can be obtained by knowing the from the in case of capillary gravity waves, and here in both the cases we have only seen that we have only analyzed the dispersion relation. Now, with these two examples I will work out one or two more example, because I said this these are all worked examples, it is a mixture of examples associated to what I have considered in my last 8 to 10 lectures. So, I am going to various aspects of the problems. Now, we have already seen the case of a wave oscillation in a tank. In a one dimensional tank. The question comes, what happens if the tank is having length and breadth? Or one dimensional tank we have seen, or we can say we have seen the case of a bay oscillation. In a we have seen that in case of a rectangular bay, one dimensional bay, Tn rather Tn is 4L by 2n minus 1 into root Gh. But if you look at the like recently in the tsunami interval time charts or in for any other regions, we always come across this is when the water depth is uniform, H is same, H is uniform. But if the water depth is varying, then there is a when H is varying over the, then what will happen to my Tn. So, it has been found that some empirical formula that a Tn in such a case can, this is the one of the empirical formula which is used 2 by 2n minus 1 into sigma n is equal to, sorry, rather I call it I is equal to 1 to n or I is equal to 1 to k such changes in the water depth, whereas gamma I by root over of Ghi. So, that gamma I is the, so k I rather k is the number of segment, here k is the number of segment of the basin length, k is the number of segment of basin length, each of length gamma I having water depth Hi. So, this is the formula normally we use when to calculate the period of oscillation of a bay during a bay oscillation, when there is the bottom depth which is varying and which has k such different segments, each segment is of length gamma I and width depth Hi. Now, this is one result which is in fact in the tsunami interval time charts many times this kind of results are used. Now, I will go to a, this is a one dimensional result. Now, what will happen in the, if I just consider the case of a two dimensional basin. In case of a two dimensional problem, suppose start with a basin. Suppose I have a basin, wave oscillation in a basin. If I have a basin oscillation and the basin is of length A and breadth B, length A, breadth B and depth, basically I mean depth is H. So, in that case we will have, if I look at the shallow water equation, so it has to satisfy del square eta by del x square, because this is the wave equation, del square eta by del y square 1 by c square del square eta by del t square, where c is root gh. C is root gh. Then in this case, if I assume my eta is of this form, eta xy e to the power I omega t, then also it will satisfy a simple relation del square, because I am separating my eta by eta bar. So, it will del square eta bar by del x square plus then this will give me plus k square eta bar is equal to 0. This becomes the independent time in there. Eta bar is the special component of the surface elevation. And then we can see that because I have a basin which is length is L and breadth length is A and breadth is B. So, what will happen? This is the plan view. Then I have what will happen by del eta by del x will be 0, because horizontal velocity is 0, and from that we can get del eta by del x is 0 at x is equal to 0 and A, and again del eta by del y will be 0 at y is equal to 0 and b. These 4 conditions it has to satisfy. So, that means we are solving this equation subject to this, because these are the 4 conditions on the 4 sides of the wall, they will be, it will satisfy. And here this is 0 less than b is less than y, here a is less than x is less than 0 less than x is less than a. So, if I look at this, then one of the typical solution of this equation will be the reduced wave equation will be eta xy, that means eta bar xy sigma m is equal to 0 to infinity a m n cos m pi by a into x into cos n pi by b into y. Eta bar xy will be this. And again we can see that, because if this has to satisfy the reduced wave equation, then it can be easily seen that my k square is equal to pi square m square by a square plus n square by b square. This is my k square. K has to satisfy this relation. And further we can see that by, because c is lambda by t and c is nothing but root gh. So, we can see that my t is lambda by root gh, and if I substitute k is 2 pi by lambda, and that will give me 2 by root gh into m square by a square plus n square by b square. So, this is what my t becomes. And here t is now no more, because t depends on both the modes of oscillation. One is the associated with the horizontal direction, one is associated with the, because it has along the x axis, this is the wave mode, and this is the wave mode along the y axis. So, in the process my Tmn depends on this. And if you look at this, then when m is equal to, in particular we can see when m is equal to, so we have the Tmn, it depends on the waves that oscillates in the, and here in the process this eta bar, it has to, because it will all depend on m and n. So, there will be 2 summation, because m will vary from m is 0 to infinity, this is also 0 to infinity. So, there will be double summation. In the same way, suppose I look at a bay. If I look at a bay which is open on one side, then suppose this is the x is equal to 0, or this is x is equal to 0, and this is the line, this is y is equal to 0, this is y is equal to B, this is x is equal to 0, this is x is equal to A, and suppose this side is open, this is open side, then this is a Bay oscillation. And again in this case it will satisfy the same similar wave equation, and we can see that in this case also we will have eta is equal to sigma m n, that is a m n cos m pi by a into x into cos 2n plus 1 by into n pi by b to be something like this into y. So, this will be the into cos omega t. This will be the nature of the wave eta. And again if you look at the Tmn, in this case the Tmn will be 2 by root gh 1 by m by a square plus 2n plus 1 by 2 into by b square, rather something like this. It will be check, this can be checked. So, this is in case of a Bay, and here it depends on the modes of oscillation both along the x axis as well as along the y axis, because it is a 2-dimensional basin. In case of a 2-dimensional basin. This is in case of rectangular basin. What happens in case of, if I look at the case of a circular basin, circular lake? In case of a circular lake, I will not spend much time on this, but I will briefly mention that if the bay becomes circular, then instead of xy, it will satisfy, if in r theta coordinate I will write my equation of motion del square eta by del r square plus and if I write my eta, r theta is f of r e to the power I s theta, just a simplification assuming that certain symmetric in theta, then I will have, it will satisfy in f del square f by d r square plus 1 by r df by dr f square minus a square by r square, f is 0, and that will give me and this gives me my f will be of this form as j s k r into cos s theta or sin s theta, one of them. So, this will be the general form of the eta, and again this will be the general form of eta. Eta or theta will be of this form. This can be easily checked. In fact, this can be found in most of the textbook on what ways. And once this is this, so what will happen for the, if I say that del eta by del r is at r is equal to a on the boundary is 0, and that gives me, it will give me j s prime k 0 for s is equal to 0 1 2, and it can be easily seen that particularly when in case of s is equal to 0, j 0 prime k is 0, that is nothing but j1 k 0, and this j1 k 0 has many roots. It is because j1 k functions, the functions are like this. The function behaves like this. So, it will have zeros are here, 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 here on this axis, although it decays at far field, but finite amplitude near the wall, and it decays, but it will have many roots. But if you look at what will happen to k, then we will see that this infinite number of roots will give us infinite modes of oscillation, and because that will once you get infinite mode of oscillation, that is what we are seeing also in case of a rectangular basin or in case of a rectangular bay, whether it is one dimensional or two dimensional. So, and here for AC you have taken the case of 0. If you take AC is equal to 1, 2, 3 onwards, then also we will get, then we will also get several such values, for because for each S you have get the corresponding j s prime k 0, and then you get, if you look at the solution of those j Bessel functions, then you will get infinite many solutions. That will give us infinite mode of oscillation, and so whether any closed or open basin, whether of any kind of a geometry, whether it is circular, whether it is rectangular, whether it is open basin, whether it is a closed basin, whether it is one dimensional, whether it is two dimensional, we have several modes of oscillation, and in most of the cases the first few modes of oscillation plays a significant role. We have earlier seen in case of a one dimensional bay or basin, now we have seen the same thing in case of a two dimensional bay basin as well as in case of a circular basin, closed circular basin. So, this is a, and in fact, in case of the difference is, in case of a two dimensional basin you have, or a bay, you have two modes of oscillation, one is in the horizontal direction, one is in the two direction on the, because on the xy plane, if you take the surface plane is the xy plane, then along x axis you have a one mode of oscillation, along the y axis again you have another mode of oscillation, and the combination becomes more complex. So, and again in case of a circular case, we have seen that further the in case of a circular basin also, we have seen the first dominating mode of oscillations are the first few modes of oscillation also, because of the, and that is very natural from the, that is clear from the roots of the Bessel functions. And these three examples today on Bay and Bessel oscillation has given us a very good idea about the case of a two dimensional basin oscillation, and the other examples what I have discussed today gives us a very good idea about various aspects of problem analysis in case of water waves, particularly the Kepler gravity wave motion problems associated with, when we have calculated that, we have found out the minimum of group velocity or the phase velocity that has given how small a wave length of a wave can be, and we have seen that in these two problems. And with this today we will stop here without much discussion today. In the next classes maybe we will talk about some of the disturbances that propagates at the surface or at the bottom, how this bottom and surface disturbances affect the wave motion in case of a gravity wave motion. And also I will talk to you briefly about a little about the finite amplitude wave theory before completing the discussion on wave motion. With this today let us stop here. Thank you.